Let us continue our journey to make our questions more complex and relevant. And for this we now turn to the Grover algorithm. This is usually labeled as a quantum search algorithm. And this indeed provides some useful context, upon which I will expand in a minute. But let me first explain what this algorithm does in terms of functions. Here we still have functions f of x, for which the input are n bits, and the output is just a single bit. So there are curly n different inputs x, and what we are stipulating now is amongst these, curly m give the result 1. And so the remaining ones give the result 0. And now, based on our experience with constant and balanced functions, one very natural question would be how many of these values here are 1, so what is the number curly m? But this is not what we are going to address here, because this is known as quantum counting. And for this we will need the quantum Fourier transformation, so we will return to this a little bit later. So here we are actually going to assume that curly m is known, but what we are interested in is to find one of the instances x for which f of x is equal to 1. This can be placed into the context of a search when we consider a database of size curly n. And in there we have curly m items that match a certain key. So we call these matching items. And these are simply characterized in terms of a function f of x. So the matching items are the ones for which f of x is equal to 1. So our task will be to find one of them. And we want to do this, of course, in as few steps as possible. Well, when the number of matching items is quite small, and we try to find these classically by just looking randomly at the different items in the database and asking whether f of x is equal to 1 for them, then we need of the order of curly n divided by curly m different attempts. And the idea of the Grover algorithm is to reduce this number of steps significantly by making use of superpositions. Indeed, what we will achieve is to reduce this number to the order of the square root of curly n divided by curly m. So for instance, when the ratio between curly n and curly m is of the order of 10,000, so that we need 10,000 attempts on average in a classical search, then we will reduce it in the quantum search to the order of 100, which is indeed a significant speed up. And we will achieve this using function gates. And indeed we will use two different types of function gates. One representing our function f, so this really represents our database, and another one representing a certain function p. But this function will be fixed. So this function gate takes n bit as an input and returns one single bit. So we have one single bit down here, and up has exactly the same structure, where p of x is again a function that just returns a single bit, namely 1 exactly when x is equal to 0, so all the n bits in the input are 0, and 0 in all the other cases. We are also going to make use of Hadamard gates to act on all these quantum bits. All these elements will play an important and distinct role in our quantum algorithm, so they will become part of a very specific quantum circuit. This quantum circuit implements a beautifully simple and ingenious strategy which has a very nice graphical representation. So instead of just writing down this quantum circuit, we are first going to develop the corresponding graphical picture. For this we are going to draw down a two-dimensional plane spanned by two states, capital X and capital Y. And here the state capital X represents all the matching items. So all the curly M values of X, for which f of X is equal to 1. So it is a sum of all the corresponding computational basis states. And the state capital Y represents all the remaining items. So all the curly N minus curly M values of X, for which f of X is equal to 0. And hence it is this sum here. And our goal will be to bring our quantum system as well as possible into this state capital X, so that when we then make a measurement in the computational basis, the values that we read off for little x will correspond to one of our matching items. But of course initially we have no knowledge about these states capital X and capital Y because they depend on the function f of x. So we will start out with a different state, which is independent of the function f of x, but also lies in this plane spanned by x and y. And this state is the state capital psi. So our familiar superposition of all states in the computational basis so this state here. And this can indeed be written as a superposition of the states capital X and capital Y. For this we just need to introduce some suitable factors. And these factors simply make sure that all the computational basis states appear with the correct amplitude. So this is then the sum of all the states with the correct amplitude in front. This expression verifies that the state capital psi indeed lies in the subspace spanned by the states capital X and capital Y. This state capital psi therefore lies in a certain two-dimensional subspace of the Hilbert space, and therefore in the subspace which has far fewer dimensions than the Hilbert space itself. And furthermore, this expression tells us where exactly in the subspace this state lies. For this we are going to express these coefficients here in terms of an angle theta. And indeed we are going to make use of half of that angle for reasons that will become clear very soon. In our graphical representation, this angle appears here. So this angle is theta over 2. Now, what is the relevance of this angle theta? Well, our strategy will be to rotate this state capital psi in discrete steps by this angle theta. And we will do this several times until we end up very close to the state capital X. And then when we make measurements in the computational basis, we have a very large chance to find one of our matching entries. Let us estimate how many steps we would need. We are going to use this expression here. So we equate sine of theta over 2 to the square root of curly m divided by curly n. And assuming again that curly m is much less than curly n, this is a very small number, so we can approximate the sign by its argument. So this means that theta is about 2 times the square root of curly m divided by curly n. And furthermore, because theta is very small, our initial state capital psi is very close to the state capital Y. And therefore, in order to succeed, we have to rotate by roundabout pi over 2. The number of steps is then given by dividing pi over 2 by this angle theta. So this comes out as this expression here. So this would be the number of steps required by this algorithm. And this is now a number of the order of 1 multiplied by the square root of curly n divided by curly m. And so with this we would indeed achieve our goal to speed up this search significantly. All that remains is to see that we can implement these rotations indeed by using function gates. As mentioned, we are going to use two different function gates, and this is for the following reason. Each of these function gates are not going to implement a rotation, but a suitable reflection. And these two reflections will combine into the desired rotation. This will work out in the following way. We still work in this plane spanned by the states capital X and capital Y, and in there single out the states capital Y and capital Psi. So these two states here. And in there we are then going to implement two reflections, one with respect to the state capital Y, and this is then followed by a reflection with respect to the state capital Psi. And as indicated here, this will indeed amount to a rotation by the angle theta. Here we see this immediately for our initial state capital Psi, because the first reflection brings it onto the other side of the state capital Y, and then we have this angle theta here. And the second reflection is with respect to the state capital Psi, so brings this state over here. So altogether this amounts to a rotation by the angle theta. And now we demonstrated this for our initial state, but the combination of any two reflections is always a rigid rotation, so this indeed applies for any state in this space. So what we really need to do is not to think about rotations but reflections, and we need to translate these reflections into operators. But fortunately for this there is a very simple and general expression, and this is again based on a geometric picture. Let us consider a very general reflection with respect to a direction that we are denoting as phi. And we start out with another state that we denote as chi. What this reflection is really asking us is to decompose this state chi into two components, one component parallel to phi and another one orthogonal to this. We are going to denote the orthogonal direction as phi prime. And then we need to keep the component which is parallel and put a minus sign in front of the orthogonal one. And by this we end up with this state here. So this corresponds to the following operator for a reflection with respect to this direction phi. This is simply given by this expression here. This still involves this orthogonal direction phi prime, but we can indeed get rid of this. We can also write it in this form here using the identity operator. And this applies because in this two-dimensional space we can write the identity operator in the following form using the parallel and orthogonal directions. But again, this also has a very nice geometrical interpretation, because we can also arrive at our final state by going twice the way into the parallel direction and then subtracting our original state. Now we see that the reflections simply ask us to put minus signs in front of parts of our states, and this reminds us of the marking of states. So let us return to our function gates. So we want to use these function gates to mark states, and then we want to see what kind of reflection this corresponds to. Well, in order to mark our states, we need to place this additional quantum bit into this superposition here. And this quantum bit will indeed always remain in this superposition. We could of course obtain this from a computational basis state, the basis state 1, by applying a Hadamard gate. But for simplicity we will just start here. And then we want to see what the function gate is going to do onto the superposition of our states capital X and capital Y. Well, because of the marking of the states, what we will place in front of this are factors of plus or minus 1 that simply depend on the function f of x, and this will always be a factor minus 1 in front of all the basis states involved in capital X, and a factor of plus 1 for all the basis states involved in Y. So this is the result of marking the states, and this indeed corresponds to a reflection. And we see this because this is the same as applying the following operator to our initial state. The operator that keeps the component in the direction of y fixed and puts a minus sign in front of the component proportional to x. And this is a reflection operator as we have established above, namely a reflection with respect to the direction of the state y. So this gives us one of the two reflections that we need. The other reflection should come from the other function gate. And when we look at this, we will see that this indeed implements a reflection, but not quite immediately the one that we need. But we will also see that it is very simple to adjust for this. In the process of marking the states, this function gate keeps the component proportional to the state 0 fixed and puts a minus sign in front of all the other states. And this can indeed be written as an operator, namely this operator here. So this would be a certain operator associated to this function gate. And to see how this amounts to a reflection in a two-dimensional space, we rewrite this in our second form, namely in the form involving the identity operator I. And now we see that this indeed amounts to a reflection, but a reflection with respect to the state 0 and not the state capital psi. And the state 0 does not need to lie in the two-dimensional subspace spanned by the states capital X and capital Y. But we can adjust for this very simply. Namely, we can multiply this operator from both sides with Hadamard gates. Namely, Hadamard gates acting on all the quantum bits involved in there, and acting on the state 0, these Hadamard gates transform it into the state capital psi, and acting on the identity operator from both sides, they leave it untouched, simply because the Hadamard gates all square to the identity operator themselves. And now we see that with this adjustment, this really corresponds to a reflection with respect to the state capital psi. So all that we now need to do is to put all of these things together. We need two sets of these Hadamard gates on both sides of the function gate up. So we place another set in here, and then we join everything into one element of our circuit. Now this element altogether is known as the Grover iterate. So this has n quantum bits up here, which represent the arguments of the functions f of x and p of x. And here we have some additional quantum bits, which simply help us to implement these functions in a reversible way using these function gates. But what we see here is that in practice we can get away with just a single of these additional quantum bits. This operator here can indeed also be implemented without using a function gate, because it simply amounts to a certain fixed unitary operator in the space of the states capital X and capital Y. So we have some liberty here, but what I described is already very efficient, so we can simply stay with this implementation. When it comes to this operator, this depends on the function f, so it is indeed most naturally implemented by using the corresponding function gate. But it can also be interpreted as an operator in the plane of the states capital X and capital Y, and then it carries a certain specific name and is known as the oracle. And this then encodes our query to the database in a very direct way, because all the states in the database are collected in these states capital X and capital Y, and the query is then implemented by a minus sign in front of all the matching entries. So this Grover iterate implements rotations by an angle theta in the space of the states capital X and capital Y. And therefore we would now like to apply this a number of times, simply determined by the values of curly m and curly n, which give us a corresponding angle theta. And this angle theta tells us how many times we need to rotate our initial state capital psi, so that we end up very close to the state capital X. And we want to start out from the state capital psi, So this, for instance, we can obtain from this state where all the quantum bits are 0 by applying Hadamard gates to all of them. And in this very specific implementation, where we use function gates to realize reflections, we have one additional quantum bit down here, which is placed into a certain superposition, and this superposition we can obtain by applying a single Hadamard gate to the computational basis state 1. So we have put everything together into one big quantum circuit, and this quantum circuit indeed implements the Grover quantum search algorithm. And in summary, this works as follows. We start from these initial states here, and as a first step, transform the first n quantum bits into the state capital psi. And we can also make use of additional quantum bits to implement the required reflections or rotations, but in our implementation this was just a single additional quantum bit, which we bring into this state here. And then we apply the Grover iterate a number of times to rotate our initial state capital psi very close to the state capital X. So at this point we end up with a state which is very close to the state capital X. And then we carry out a measurement in the computational basis, and the result will be a certain number little x. This occurs with probabilities p of x, which are very close to 1 over curly m whenever f of x is equal to 1, because this is a state represented by the state capital X. But the probability is very small, very close to 0 in all the other cases, so when f of x is equal to 0. Overall, we end up with a very large probability to find one of our matching entries. Sometimes we do not quite succeed, because our final state might be very close to the state capital X, but not identical to it. And this happens in particular when our angle theta is not a multiple rational of pi. But in these cases, we can then check our result by calling the function gate just one more time. And if this tells us that the result didn't match, we can run the algorithm again, and typically we will not need to do this many times. So on average, we will then still realize a significant speedup compared to the classical case where we also just look at random. But this also highlights the probabilistic element of this algorithm, because we find our matching entries at random. So this is the Grover algorithm, and this concludes our discussion of problems related to functions for which the output is just a single bit. Now we turn to functions for which the output has more bits, and indeed just as many bits as the input. But there we are just going to look at one very important and central example, which is related to the Fourier transformation. This then allows us to define the quantum Fourier transformation, and with this we can then tackle the most important and powerful quantum algorithms that we know of.